Okay, so today we're looking at titration curves. We did do a titration lab the first few weeks of school. I don't know if you guys remember what the titration curves look like. Can anyone describe the one we did? What it kind of looks like? It's kind of, yeah, kind of like an exponential function. Here we start out, steep rise, and then we had something like that. And then our point was to find the molarity of an acid. And these are titrations. And so you were specifically looking for the middle of this steep rise. Does anybody remember what that was called? The equivalence point. And who remembers what the equivalence point was? Jasmina's batting 1,000. What was the equivalence point? What was true at the equivalence point? Very nice, Nimish. Moles. High five him for that. Moles of your acid equals moles of your base. Okay, and so what we're actually going to do today, we're going to see different types of titration curves. This is specifically a strong acid, strong base curve. I call it a strong, strong. And in this particular case, because the pH is starting low, in your beaker, you've got your acid then. And then in the burette above it, your titrant is your base. The thing in the burette is called the titrant. Okay, so that's what that curve looks like. But if I were to have the actual base in the beaker and the acid as the titrant, how do you think the curve would look? It would be up high, down low. Okay, so the curve can look like that for strong, strong. But today we're going to look at weak, strong as well, which are the tough ones to calculate, where we have a weak acid, strong base, or weak base, strong acid. And so it's going to have a little bit of a difference. It's going to look more like this and not be as dramatic. And we'll talk about the parts of that and how they're different. So today is basically calculation hell. So get ready. All right, number 9. We're going to create the curve. We're going to build the curve. So it says a titration is performed by adding 0.6 molar KOH with 40 mils of 0.8 molar HCl. So let's classify. What type of curve is this? What type of titration? Good. This is a strong, strong. These are our easy ones to calculate. You're basically going to do stoichiometry tables. We're invading. What's in the beaker in this particular case? The HCl. The moles of HCl we have throughout this entire problem, parts 1 through all the way 10, we are going to have the same number of moles. This does not change. What changes is the number of moles of base that we're adding and adding and adding. So it's kind of an invasion problem. So in this first one it says, calculate the pH before any of the base is added. So look at our acid. Our acid is a 0.8 molar HCl. Doesn't matter how much I have in there. What's the actual pH of that? How do I find it? Negative log of 0.8. And I do have some of the answers written down, but I always want you to verify that you're getting the right answer. And that looks good to me. Right? So it's a really, really low pH. Now it says, after the addition of 20 mils of the base. So what you're doing is you're invading that H plus that's in this beaker with OH as the titrant. So what does that make? Oh, that OH plus, yeah, that exists. Okay, and so what does that make? Water. So we're just going to do a stoich table and take moles of each. So let's first find the moles of H plus. We take our 0.04 liters times our 0.8, so this is 0.032 moles of that. This does not change. Okay, we're not going to ever add more acid in the titration. We're only adding base. And when we take our 20 mils of 0.6 molar, it's 0.02 times 0.6, that's 0.012 moles. So now it's just limiting reagent. Which one's going to run out first? Minus 0.012, minus 0.012. We don't care about the water. So we're left with 0 here, and we have 0.02 moles here. Okay, so we have something strong left over. We have not used, we still have acid remaining. All the base was used up. So how do I find the pH now? Divide by liters. This is where you need total volume. We had originally 40 mils of the acid, and we added 20 mils of base, so we divide by 0.06. for 60 mils. And your pH comes out pretty darn close to 0.478, right? Okay, so again, you got to convert to molarity before you actually try to take the negative log of the H plus. I guess I should say negative log for those at home. And that H plus was and then we took the negative log of that, and we got our pH. So far, so good. So we're going to keep moving along with the titration, and we're going to keep adding. Now, when it says the addition of 40 mils, it's not 420 plus the 40. You got to the 40 on the burette, so you just use 40 mils. Don't use 60. Last class, they were trying to use 60. Okay, do y'all understand that? All right. So again, we have the invasion. The original amount of acid of 0.032 will not change. When we figure out the moles of base, we're adding 40 mils. So our 0.4 times our 0.6 gives us 0.024. Does everyone know where I got that? Okay. How much do we lose? 0.0. So our base is still being used up. It's not left over yet, leaving us with 0.008 moles of H plus. Got to convert that to molarity. What's our total volume? 40 in the beaker, 40 from the burette, 0.08. So that gives us a concentration of H plus of 0.1. Negative log of that is 1. Now, has our pH changed a lot from the beginning of the titration? No. We've added almost an entire burette full of acid, of base, excuse me, and nothing's changed yet. So this is going to show you why we such a sharp rise here in a minute. It says calculate the pH after the addition of 53 mils. So our original acid is being invaded by some base. Our original 0.032 stands. But now when we take 0.053 times the 0.8, we get I got 0.032. Y'all get that? Okay. Oh, whoa. That's not right. This is wrong. No, this one's wrong. This is 0.032. And then this one was, I got 0.0318. Is that what y'all got? You said, someone said yes before, and that was wrong. So don't let me mess up. So here we lose 0.0318. 0.0318. So we're still using up the base, leaving us with 0.0002 moles of our acid left over. Divide by the total volume. What is our total volume? It's 93.2 mils, so, or just 93 mils, excuse me. So it's 0.093 liters. So we get an H plus concentration, 0.00215 moles per liter. When you take the negative log of that, you get 2.67. So we saw a little bit of a jump there comparatively, right? Okay, now let's go ahead. When we're constructing a curve like this, we have to find that equivalence point. And again, what was the equivalence point? When the OH concentration equals the, not concentration, making all these mistakes today. When the moles of OH is equal to the moles of H plus. So we know that H plus this whole time has been how many moles? 0.032 moles, right? So we need to be at the equivalence point, we need 0.032 moles of the base. So I'm going to make that blue because that's how I roll. 0.032 moles. We want to know how much volume of that is required to get to that 0.032 moles. So what was the original molarity of the base? 0.6. All right, so what's the volume? You should get liters of 0.0533 when you take 0.032 divided by 0.6. So that's how many mils. We usually convert to mils just because we don't read the burette in liters. We read it in mils. Okay, so that's how much we need to add to get to the equivalence point. So now I want to figure out, well, what is the pH at the equivalence point? For strong, we have a very specific result at the equivalence point. Does anybody remember what that is? pH is 7. Let's prove it. We had 0.032 moles here. To be at the equivalence point, what did we say? 0.032 moles. What happens here? We lose all of those ions, right? And we make water. So what's the pH then? pH has to be 7. This is only the case in a strong titration. It will not happen in a weak strong, and I'll show you why. People say, well, why wouldn't it? If OH minus and H plus are equal, there's something else that comes into play in our next titration. And I'll show you that in a second. Okay, is everyone's head still above water? I know we're moving fast. All right, let's go to number 9. Did I skip something? I think I've lost a page. I can't find where I am on my paper. Page 13. All right, I found it. Calculate the pH after adding 5 mils of NaOH past the equivalence point. So we have our H plus, we have our OH minus. Our original moles here stays the same. If we're adding 5 mils past, we were at 53.3, right? So 5 mils is 58.3. So 58.3 times the original 0.6, well, 0.0583 times the 0.6 molar gives us what? 0.035. Oh, look what's happening here. What happened this time? We ran out of acid. So now the base is going to take over. And we end up with 0.003 moles. This is of OH minus. So if we divide by the total volume, it was our 53.3 plus the 5, which is 58.3, plus the original 40, that's 0.0983 liters. So our OH concentration is equal to 0.0305. So if we take the negative log of that, we end up getting a what? A POH. And what POH did you get? 1.52. And when you subtract that from 14, you get 12.48. So what we're going to do is sketch it based on the numbers. It's a sketch, so it's not going to be exact, so don't freak out. We always put pH on the Y. So I'm just going to do it in units of 1. 1, 2, 3, 4, 5, 8, 9, 10, 11, 12, 13, because we went up to only 12.5. So 1, 2. Okay, and then how many mils we got up to adding of base? 58 or 55, 55. So I'm going to do 2s. 2, 4, 6, 8, 10, 4, 6, 8, 20, 2, 4, 6, 8, 30, 2, 4, 6, 8, 40, 2, 4, 6, 8, 50, 2, 4, 6, 8, 60. Okay, so these are mils of base. So let's go back to our first points and figure this out. Before we added any base to the acid, what was the pH? 0.1, like way down here. What'd you do? All right. Then we added 20 mils, and what was the pH? A half a unit. Oh, wow. Phew. And then we added 40 mils, and the pH was 1. Wow, look at us go. Okay. Then we added 53 So that's 42, 4, 6, 8, 50 right here. And what was the pH at 53? 2.6, so about there. Don't judge me for my graphing ability. And then we got to the equivalence point where we only went 0.3 mils past that, which in terms of how it looks is pretty much the same spot, and we jumped up to what? 7. So we barely added any more, and we were up to 7. Okay? And then 5 mils beyond that, we got up to a pH of 12. So 2, 4, 5, pH of about 12. Whatever. Okay, so this is a very distinct, strong curve where we start out really flat, nothing happens, and all of a sudden, phew, jumps up. And I should probably have filled in some more points for you, but it's going to taper off. And when the base totally takes over, we're just looking at 100% pH provided by the base. Okay, and so one thing to note is equivalence point is at 7. That's really, really important in a strong situation. Y'all feel good? Feel great. Raina feels great, everybody. What? You feel amazing? Jasmina feels amazing. Wes looks like he's going to hurt somebody. I mean, Thomas. I keep calling him Wes. Thomas looks like he's going to hurt somebody. Looks like a serial killer right now. He's got that look in his eye. All right. Next one. Now we're going to try the other situation. If you look, we have a strong base, but what's up with our acid? Weak. I'm going to call it Hockle. It's that hypochlorite, okay? Hypochlorous acid, the hypochlorite ion. So we are going to do a strong weak or a weak strong. And this gets kind of crazy in terms of calcs, but nothing you haven't done. Every single thing you've done over here to the left of the board is part of this, so you'll be fine. Calculate the pH before any addition of NaOH. So we have, again, in our beaker, our Hockle, our acid, and then the base is in the burette. So let's go ahead and calculate. How do I do that? Whoa, hydrolysis. Uh-oh, Jasmina just, everything good she said today, gone. Yeah, rice table, all we're doing is finding the pH of what? A weak acid. You said hydrolysis. No, it's not. But that's not what hydrolysis is. That's called hydration. All right. Yeah, and I said the Pope. I don't know. Okay, so we're going to take the Hockle and add it to water in a rice table. One piece of information you need is the Ka for this. The Ka for this acid, which you're going to write about 1 billion times in this one problem, is 3.5 times 10 to the negative 8th. So HOCl, we're going to make the alkyl ion plus H3O plus. Our original concentration, they told us, was 0.35 molar, 0, 0. So just keep working, everybody. Work, work, work. I don't have this data written down because the last class kind of did it on their own. So I'll need some X's here in a second. I got interrupted and had to leave. So X squared divided by 0.35 is equal to 3.5 times 10 to the negative 8. And this answer is going to be a little bit off. I don't know why. What did y'all get for X? Okay, and then if we take the negative log of that, yep, that's what they got. 3.96 is our pH. Okay, so what's different about this pH and the last pH? There is kind of a distinct thing when we're dealing with weak versus strong. Yeah, it's not such an extreme pH. It's not super high or super low like in the strong situation. Okay, calculate the pH after the addition of 5 mils of base. We are adding the base, which is strong, to HOCl. What kind of equation is that? What does this fall under? It's an invasion equation. That's the new term we're calling it. So we're going to invade our Hockle. We'll always, I don't know, I feel like we should write the invader first. We're going to invade with OH minus, and we're invading the HOCl. The HOCl moles will never change, so let's find those moles and pretty much commit them to memory. 0.0084 is what I got. We have 0.350 times 0.024. 0.350 times 0.024, okay? Now, after 5 mils of base, it's 0.005 times 0.2, so that's 0.001 moles of the base. And what is, I should finish the equation, would be a really good thing. Alkyl plus water, alkyl minus. So we have none of this at first. How much are we going to lose? 0.001 minus 0.001 plus 0.001. We get rid of all our base. Our base is used up, leaving us with 0.0074 moles of this and 0.001 moles of that. Okay, the war's over. What do we have left over? What kind of system? This is a buffer left over. So for the ease and time, are you guys okay with understanding why we don't have to divide both of these by liters? Okay, because of Henderson-Hasselbalch, we can just plug in. So pH is equal to the negative log of 3.5 times 10 to the negative 8, which is our Ka, plus the log, which number goes on top? The ion, which is 0.001, which is alkyl, divided by 0.0074. Again, this is supposed to be concentration here, but because we would be dividing both those numbers by the exact same volume, it's not required. So the pH you should get is 6.59. All right, so do you see a difference already with a trend in this curve compared to the last one? What's different? It went up more significantly at first, okay? It didn't like have no change, but we're going to start to see some stuff going on here. So now we're going to calculate the pH after the addition of 15 mils of base. So again, we're going to have an invasion equation. This whole titration is an invasion. We just keep adding more and more strong and more strong. Plus Hockle gives us alkyl minus plus water. So our original acid never changes. Our OH minus is 0.015 times, I forget, what was the molarity, 0.2? 0.2, so that's 0.003. So we're going to lose 0.003, lose 0.003, gain 0.003. So what did we make? Another buffer. Keep making buffers. That's interesting. What do buffers do? Stabilize pH. Yeah, once we hit the buffer zone like this, you're going to start to see a flattening out of the pH. So pH is equal to negative log of 3.5 times 10 to the negative 8 plus the log of what? Good. Ion over, I'm just going to be like one of those professors in college. I'm not going to move. I'm just going to stand here and write. There are those, believe it or not. All right, 7.2, did y'all get that answer? Cha-ching, correct. Okay, calculate the pH after the addition of 25 mils of the base. So the invasion continues. Poor acids getting bombarded. Leave me alone. This is 0.0084. 0.2 times 0.025 is 0.005. So we're going to lose 0.005, lose 0.005, and gain 0.005. So base is still running out. The acid's still holding strong. 0.0034, and 0.005. So what do we have? A buffer. Again, pH is equal to the negative log of 3.5 E negative 8 plus the log ion 0.05 acid all right, 7.62 looks like a wiener. All right, good? Is everyone okay? Greer does not look happy. She's like, really? Do we have to keep doing this? All right, we're almost done. Let's keep moving and grooving. 7, calculate the pH after 35 mils. Well, let's go back, by the way. I want to see. So we added 15, we're at 7.2. We added 25, we're at 7.6. So you see how we keep seeing buffers, buffers, and as soon as we started seeing buffers and buffers, that pH is slowing down. So we're going to continue at this slow pace until the acid gets overwhelmed, and you'll see that happen. So the pH after 35 mils of the base. So invasion equation. What am I doing? Plus water. So this is 0.0084. What's the amount of moles of base? 0.035 times 0.2. Good. 0.070. 0. So now we lose. Acid's still holding on. Way to go, acid. 0.0014 and 007. And his doubly awesome counterpart, Hockle. He's twice the man that 007 is, because he's 0014. All right. Still have a buffer, right? This is when I'm doing these problems too much. Things start to be funny that aren't really funny. In my mind, what I just said was hilarious, and y'all just sat there. So 3.5. I keep wanting to write acetic acid's Ka. 3.5 times 10 to the negative 8 plus the log. Who's on top? 007 or 0014? 007. Okay, and when you solve, did y'all get 8.15? Yes. So your test will be a lot like this, but you're not going to have this part. Just saying. Yeah, so don't get used to it. I'll just give you this handout. That'll be good. You know what? People would still miss, though. I promise you. All right. Jasmina would still miss. All right, let's see. Now we need to calculate the volume of base needed to reach the equivalence point. So our Hockle was always and forever 0.0084 moles. So our base, I can't remember if it was sodium or potassium. It was a 0.2 molar. We need to be at the equivalence point. How many moles? So we want to know what volume. 0.0084 divided by 0.2 comes out to be 0.042 liters, right? So we need 42 mils to get to the equivalence point. So now we're going to see what happens when we're at the equivalence point. Last time, the equivalence point, those two things got together and made water, and the pH was 7. We were fine and dandy. We didn't even have to use our calculators. But in a weak, strong situation, we have a different story. So let's just write out the equation to prove it. Hockle makes alkyl minus an H2O. Make some room here. You're going to need some room. I know. So this is 0.0084 because we're at the equivalence point. So we're going to lose 0.0084. Why don't we have a pH of 7? What did we do when we lost? Didn't we gain some alkyl? Doesn't that create a pH? Yes. Through what, Jasmina? Through what? Very nice. I was so glad. I was afraid she was going to mess up again. Got nervous. So we have 0.0084 moles of this. So now what's left over is the need to add that to water and do a rice table and be in a hydrolysis scenario, but we can't put that in a rice table until we divide by what? The liters. That's why we needed, people are like, why do you need to know how many mils? Because this is why. We got to know how many mils were required to reach that equivalence point. And we said it was 42 mils. And the beaker had 20 in it, so 24. So that's 66. So 0.066 liters. So that comes out to an alkyl concentration of 0.127? 0.127 moles per liter. So now what do we do? Rice, baby. Dun, 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 dun. Y'all know Vanilla Ice, right? Okay, just checking. You what that song? You are familiar? Stop, collaborate, and listen. Ice is out with a brand new invention. It's a great song. Did y'all see the, I can't believe I'm doing this on tape. Did y'all see the thing where I think they were, I don't know if he was being sued or people were questioning that it sounded too much like Queen's Under Pressure, the intro? And he was like on the video, no, Queen's is dun 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 da 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 da. Ours is dun 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 da da da. I mean, it was so funny. It was like, dude, they sound exactly alike. What are you talking about? Anyway, I enjoyed that. All right, so we're going to take alkyl and put it through hydrolysis. So we're going to add it to water, and we are going to create alkyl and OH minus. Our original concentration is 0.12700 minus X plus X plus X. 0.127 minus X, X, and X. We can drop it because it's negligible. And so, oh, I'm running out of room. I'm going to take it down here. We get X squared over, but I have a problem. I have an OH and I need a PKB. So we're going to take 1 times 10 to the negative 14th, and we're going to divide it by 3.5 times 10 to the negative 8. And when we do that, we get X squared over 0.127. The actual PKB, I thought I had it written down. 2.90 negative 7. And so our X, which is equal to our OH concentration, comes out to be 1.9. I can't tell if that's a negative 6 or a negative 4. 1.9 times 10 to the negative 4. And then, therefore, our POH is equal to 3.72. And the pH then is correct at, is it correct? No, this one's wrong. This is 10.28. I don't know why that's messed up. 10.28. Yeah, I would do that on a test. If I gave you a test with answers like that, I'd on purpose give you one that was wrong and make you figure out. I told you all about the test I wrote that had all the same letter but one. Did I tell you that? Yeah, they were all B's except for one. There were 35 questions. Yeah, and most people just went ahead and made it B. They were wrong. It's so awesome. It was fun. It was good times. After the first, like, 5, you saw people just fidgeting and really uncomfortable. Like, what's going on? Yeah, it was bad. Oh, really? Might have to give that a whirl. All right, the last point before we graph it and talk about the differences between the two. Calculate the pH after adding 5 mils of NaOH past the equivalence point. So finally, good old NaOH invader is going to take over. So we're still at here 0.0084. 5 mils past the equivalence. We were at 42 mils, right? And we added 5 more. That put us at 47 mils of 0.2. So 0.047 times 0.2, 0.0094. So we're going to 0.0084, 0.0084 plus 0.0084. But what can you tell me? Invader wins because it's strong. So this is 0.0014, and this is going to win. Strong wins. This is moles, though. Before we can take the negative log of it. Did I do something wrong? Oh, 4 minus 4. 4 minus 4 is 0. Okay, divided by, all right, now we got to figure out our total. We had 47 plus the 24, right? So that's 71.071 liters. Gives us an OH concentration of 0.0, gosh, that is really, really basic. And then taking the negative log of that, POH comes out to be 1.85. And when you subtract, that worked out. Don't know why the other one wasn't right and that one was, but. All right, are y'all okay with the calc part of this? I know it was a lot. You won't have more than 2 of these on your test, I promise. I'm kidding. You won't even have 2 of these on your test. Raina's eyes as soon as they popped out of her head. It'll be okay. Just trust me. You need to go through this hell to appreciate what'll be on your test. It's not going to be bad. All right, so now we're going to sketch. We always put the mils of the titrant on the y-axis. Why not the mils of the beaker? Because it doesn't change. It wouldn't be a very fun graph. It would just be 1 point. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, and then I guess I'll do it in 5s again. That was pretty nifty. 2, 4, 6, 8, 10, 2, 4, 6, 8, 10, 2, 4, 6, 8, 10. God, my accuracy here is just phenomenal. My scaling. 10. I think I'm done. I don't need any more than that, do I? 20, 30, 40, 50, 60. No. Okay, so let's go back. Before we added any base, what was our pH? Pretty much 4, right? So we were pretty much here. Okay. After adding 5 mils, we were about 6.5. There. All right. After adding 15 mils, we were at 7.2. Whoa. Okay. After adding 25, no, we weren't at 7.2. Yeah, we were. After adding 25 mils, we were 7.6. 10, 25. Barely any. Probably went too much on that one. After 35 mils, we were at 8.1. Okay. And then we were at the equivalence point, and that was at 42 mils. And what was the pH at the equivalence point? Oh, whoa, look at that rise right there. Okay, that is so not over the right volume. It's more here, 10.3. And then 5 mils past that, we brought it up to 12. And then it would kind of like do that. Okay, So let's take a look. When you first start out one of these titrations, you're going to have an initial little doot. Okay, that initial little part is creation of your conjugate, getting you into the buffering region. This to here is pretty much the buffer zone. Not the danger zone, not Top Gun, the buffer zone. All right, so here's our buffering region. Do you see how our rise is not quite as sharp and sheep? Isn't that great? Sharp and steep. The equivalence point is not at 7, okay? You're going to need to be able to predict, though, based on the strength of the acid or base, the range of the equivalence point, which is not hard. If your titration is a strong base, weak acid like this one, the equivalence point pH is above 7 because it's the strong base that wins, right? What if it's a strong acid, weak base? Below 7. So I can, and I'm going to do this tomorrow, I'm going to throw a graph up there and I'm going to say, tell me, is that strong, strong? Is that weak, strong? If it's weak, strong, I'm like, what's strong, the acid or the base? And so you're going to be able to just to look at the curve with no labels and tell me about that. Okay? Don't look so confused or sad. I can't tell. I can't tell the difference between your confused look and your, oh, okay. She's holding in her excitement, she says. Now, there's one other part about this curve that's really, really important that is not in existence in a strong, strong. It's called the midpoint. The midpoint is the point. Now, let's see if you can remember. We've already kind of talked about this. When half of our acid is used and converted to that. When did we see that happen? With the 007, 0014. No, that, but not, okay, if we had 10 and we used up half, when was this? It was the lab. So they canceled out, right? So what did your Henderson-Hasselbalch look like in the middle of this? pH equals pKa. That exists at the midpoint. Why is this important? Sometimes on the test, they'll give you a graph, and they'll say, what's the Ka of the acid? And you're like, what? What are you talking about? What's the Ka? Well, you find it by going to the midpoint. Let's do that. Where was our equivalence point? At, give me the mils. 42 mils. What's 42 divided by 2? Halfway. 21. Go to 21. This right here, oh, that's not really 21. That's 21. This right here is the midpoint. What's the pH-ish at 21? 7.2-ish, okay? So if we know the pH at the midpoint, how do we find the pKa? The pH is the pKa. Sorry, how do we find the Ka? 10 to the negative 7.2. Someone put that in your calculator. Let's see how good I got. Last period, I like nailed it. What did you get? Okay, that's not as good as I did last time, but 6.31. Remember, this is me doing a hand graph. At least I'm in the right magnitude. But they could actually give you something like that and say, what's the Ka of the acid? And you're like, I have no idea. Go to the equivalence point, find where it halfway is, and then you can determine from that pH what the K is. Do y'all understand why that is? Because at that point, half of this turned into this, making these equal concentrations. So they fall out of Henderson-Hasselbalch. Got it? Okay. Last thing, let's just make our list. In conclusion, this is where we wrap it up. Weak, strong versus strong, strong. Let's list some strong, strong characteristics of graphs. Equivalence point is 7. Therefore, over here, not 7. Yeah, I can't even spell. So if you have a strong acid, what's the equivalence point? Strong base, gosh, greater than 7. Okay, that doesn't confuse people the way I wrote that. And then, what else when you look at it? This has a sharp rise. This has a buffering region. Now, in both cases, though, the equivalence point will fall. There is kind of a rise here. It does fall in the middle of this rise. And in the previous, it falls in the middle of the sharp rise. So it's still kind of the same in that respect. One more thing I'm looking for. Well, oh, this, okay, I forgot about that. But this one has a midpoint. There is no such thing as a midpoint in a strong, strong situation. Okay. Oh, this is also known, I didn't say this earlier to the other group, but some people call it the halfway point. Same thing. Last thing, looking at the starting point. Or higher if it's a base. So extreme pH start. Super high or super low. I'll put less extreme start. So tomorrow we'll just kind of review a little bit. In class, I'm going to do that problem, and then you'll take your quiz. And that's all we'll do tomorrow, okay? Done.